Okay, let's get started. My name is Steve Cranmer. I'm a professor in the APS department at the University of Colorado Boulder. This is our first lecture in the spring 2016 HAIL COLLAGE program course. COLLAGE stands for Collaborate Graduate Education Program. Our course for 2016 is going to be Topics in Solar Observation Techniques. We'll be looking at a whole range of different ways that we observe the sun. The general idea is to have these advanced solar courses that are distributed to multiple universities, and hopefully our video flipped classroom technique is a useful way of doing that. So in this first third of the course, part 1 of 3, I'll be talking about observing the solar corona, mainly the solar corona, above the solar limb, basically looking off to the side of the sun, and observing the plasma in the regions far above the solar surface. In the later parts of the course, we'll be looking at more direct observations of the solar photosphere, but we're starting off here with observing above the surface of the sun. So this first lecture is sort of an introduction, but I wanted to first give a brief overview of my entire third of the course, part 1 of 3. The overall goal, as you see there, is to introduce you to this whole world of off-limb solar observation techniques and diagnostics, both how we do it and what we get out of it, different measurements of the actual plasma in the solar corona. So I'll start off with lectures 2 and 3. There'll be some surveys of basic topics in radiative transfer. How do we define the radiation field? How do astronomers do it? How do physicists do it? And how do we sort of merge those two different languages into a common description? And how does the radiation interact with matter? How does the polarized radiation field interact with matter? A whole bunch of things that you might have seen in earlier courses, but we're including them here as sort of a backup in case you haven't seen it before. The rest of this section of the course is a description of the solar corona. Why do we have to occult? Why do we have to block out the bright solar disk to see the much less bright light from the solar corona? Why? How do we do that to get the most successful observations? And then what are the observations? What do we actually see? Parts 3 and 4 on the screen there, basically looking at the visible continuum. Basically that's where we start. With the total solar eclipses. Seeing with the naked eye, we see the visible continuum. What can we get out of that? And then how do we break up the spectral energy distribution into specific lines, both in the visible and all the way into the UV and X-ray, and down into the infrared as well? What are all the diagnostics there? At the very end, I'll say a few brief words about how we actually bridge together this whole topic of looking at the extended solar corona with telescopes, with the other big way of investigating the extended parts of the solar corona, and that's by sending spacecraft with direct particle and field measurements into the plasma to directly measure, these so-called in situ techniques. And the range of overlap between those two techniques is now getting bigger and bigger. Solar probe is going to be going into the corona, and our heliospheric imagers are going further and further out into the solar system. So we're really hoping to get the benefit of complementarity in both of those types of observations. In this particular lecture, this particular video, I'm going to be sort of giving a brief historical overview of how we got here. What are the observations that have been made since the 1800s or so, and a quick overview of the different regions that we're going to be talking about. Sort of an overview of the nomenclature, essentially. Okay, so let's get started. I always like to start off with these beautiful images of the solar corona taken during total eclipses. You can really see all sorts of interesting things going on. Of course, you can really see the fact that the plasma traces out the magnetic field lines of the sun, all of these curved structures, some of which loop back down, some of which are sort of stretched out by the solar wind. You can really see it very clearly. This is an image taken by Miloslav Druckmuller, who has a wonderful website you can see there, and he's been doing eclipse observations for the past decade or so, and they just keep getting better and better at each eclipse. As far as the nomenclature goes, there's all these different regions from the sun all the way out to the interstellar medium that we give names to. They're sort of, in some ways, they're discretely defined. In some ways, they're They're ambiguously defined. For example, the extended corona and the solar wind sort of merge into one another. I'm just sort of showing a cartoon here. It gets a bit more quantitative when we look at something like the temperature as a function of radius above the surface. And I can start to show you what that looks like. We've got a log scale of temperature versus distance, heliocentric distance from the center of the sun. The part of the plot that's shown now is the solar interior. That is a model of the solar interior that's been validated from helioseismology. The core of the sun is 15 million Kelvin or so, and it drops to about 6,000 Kelvin at the photosphere. That's the drop that you're seeing there. Of course, we know that the solar corona occurs quite rapidly above the solar surface. The temperature boosts back up again to about 1 million degrees. Still one of the big unsolved problems in solar physics. How is the corona heated? That's not quite the topic of this course, but we'll be getting into some of the observations that tell us more about what's happening there. All we know right now is that the temperature goes back up to 1 million degrees, and because of the low density and the ionized gas is a very good heat conductor, the temperature stays constant for a while. As we go to the right here, we're getting bigger and bigger in terms of spatial scale. So we can see that the temperature stays about 1 million degrees for several solar radii. As we keep going out, the temperature eventually drops to about 10 to the 5 degrees by 100 solar radii or so. The Earth is sitting up there at 215 on the x-axis, and I'll show you that in a little bit. Eventually, the temperature goes down to about 10 to the 4 kelvins, starts to come back up again as pickup ions that are sort of bleeding in from the interstellar medium start to energize the plasma a little bit. And eventually, we get the termination shock that you can see there at a distance of a few times 10 to the 4 solar radii. We should actually use astronomical units out there, where the temperature boosts back up again. Spacecraft have now flown through this region. The heliopause is where it goes back down, and we start to go into the interstellar medium above that. So what I can do is sort of move this up and show you some more details. Now, on this same scale, we can actually look at the outflow speed of the solar wind. So on the bottom, it's now a linear plot on the y-axis, and we can see that the solar wind gradually accelerates over the first 10, 20, 30 solar radii to a terminal speed, and it essentially coasts out through most of the heliosphere, and it drops from supersonic to subsonic at the termination shock, and essentially decreases to very small values. And you can actually see that what I've plotted here is the velocity along the direction that the sun is moving throughout the interstellar medium, because above the heliopause, the velocity is negative. The velocity is essentially coming towards us. It's towards the sun, which is the opposite direction as the solar wind going away from the sun, so it's portrayed as negative here, at a few tens of kilometers per second. So this aims to be a sort of a realistic picture of what's happening along that line of sight from the sun into its ram direction throughout the interstellar medium. For context, I wanted to show you a few extra little places, some of the inner planets, Mercury, Earth, Jupiter, as we go into the outer solar system. Pluto is there at almost 10 to the 4, or 40 or so astronomical units. The current location of Voyagers, the Voyager probes, is out there around the position of the heliopause. It's essentially the place where the subsonic solar wind meets the subsonic interstellar medium gas, and there's a sort of a contact discontinuity there. And the Voyagers are exploring that region of space right now. Now, this whole temperature plot on the top is an abstraction. It's essentially a model. And the one thing that it ignores is the fact that once you get above the surface of the sun, the densities drop to a low enough level that the particles aren't colliding with one another very frequently. So the different species can have different temperatures. And that's what I want to show you here, just again, as an introduction to what's going on. You've got, it's a dominant hydrogen plasma, so there's protons and electrons that make up most of the plasma. Then there's heavier ions, and they can all have different temperatures. In the lowest density region above the polar coronal holes, we'll get into what all these things are soon, it sort of looks like what I've plotted. The heavy ions are the hottest, The protons are slightly hotter than the electrons, and that persists all the way out into interplanetary space. The observations are still getting better and better, and we're still getting a better feel for all this. Solar probe, we hope, will fill in a lot of these gaps as it goes into about 10 solar radii, and that's in 2018, 2019. Exciting times. So a lot of these things have been learned from a complementary approach of looking at telescope, remote sensing observations near the sun, and in situ probing of the plasma further away from the sun. And as I've been talking about, there's traditionally been a gap between about 10 and 100 solar radii. The innermost distance that spacecraft have gone has been about 60 solar radii so far, and the telescopes that are looking further and further from the sun, it gets much harder and harder because the light gets much dimmer and dimmer. So there's been this gap, but again, we're starting to bridge that gap in the 21st century. So that's what a lot of this course will be about. This green piece, on the left here, the remote sensing above the surface of the sun. I also tried to extend it a little bit below the surface of the sun too, to indicate what helioseismology has told us. But it's mainly the regions above the surface that we'll be looking at here. Okay, just a quick summary. Again, I've mentioned a lot of these things already, but I just wanted to lay out all the different, the overall different ways that we observe the sun in these different regions, and they're sort of organized in increasing heliocentric radius r listed here. And we'll be using the solar radius as our unit of measure. It's a very convenient unit. So most of the coronal heating happens very close to the sun, within a few tenths of a solar radius of the surface, so about 1 to 1.3, 1.5 solar radii. Most of that is done with direct imaging. We could do a lot better by blocking out the disk of the sun to see these regions, but a lot of the times we just look at the whole thing, the sun and the surrounding regions, because it's still pretty bright. But once we get above about 1.5 solar radii out to 10, 20, 30 solar radii, you really do have to block out the disk of the sun. You have to occult the sun with either naturally, wait for a total eclipse, or use an artificial eclipse, which is a coronagraph or a heliospheric imager type instrument that observes these regions. We'll be talking a whole lot about those as we go. This outer extended corona region that's only accessible with coronagraphs and eclipses is interesting, again, because of the collisions between the particles become very infrequent, and it goes from a very collisional one fluid case to a collisionless multi-fluid kinetic case where each species can sort of do its own thing in terms of flow speed and temperature and all the other properties of the plasma. And it's also, this region is also where most of the solar wind acceleration is happening, as you saw on the previous plot. So if we want to understand the acceleration of the solar wind, we really have to observe this extended corona region. And of course that bleeds into what we call the inner heliosphere. The orbit of Mercury is in there at about 60, and we've been probing that region from Mercury on out with in situ probes. Now in green there, I also have radio sounding. That's another very fruitful means of observing the extended solar corona and the inner solar wind. I'll be talking a little bit about that at the end of the course. Radio waves can pass through the corona and learn a lot about the plasma that's being probed by those radio waves. So we'll talk about that a bit too. Okay, I also wanted to give a quick list of all the different types of things that we can measure. What can we actually get by looking at these photons that are emitted by the extended solar corona? Well, basically by looking at the total number of photons, that basically can give us an indication of the density. How many particles are there that are emitting or scattering photons. By looking at Doppler effects, we can look at the plasma velocity. You can also use imaging for that if there's structures that are being accelerated out, low contrast structures that are being accelerated out passively, and we see them as intensity variations, intensity modulations that are moving out. So by looking at motions in the sky and motions in the line of sight direction, we can essentially pull out all three components of the vector velocity of the plasma. We can look at the temperature. There are all sorts of ways of probing the temperature via both spectroscopy and imaging. And some of the most advanced techniques can even tell us things about departures from Maxwellian velocity distributions. Again, as you go up high and it becomes collisionless, then there's no reason for it to maintain a Maxwellian velocity distribution anymore. And we can now probe that with a lot of these different diagnostics. Of course, there's also the magnetic field. In later parts of this course, you'll hear much, much more about the Zeeman effect and the Hanley effect for telling us about the magnetic field vector. And then also there's variations on all sorts of scales from fractions of a second to hours, days, months. We can see fluctuations in all these other diagnostics that can tell us about the presence of waves, shocks, eddies, jets, all these different types of fluctuations throughout the plasma that might be very important for producing and maintaining the coronal heating. There's also all sorts of other indirect measurements. We can measure the properties of dust with some of the properties of the spectrum, the visible light spectrum, the so-called F corona that we'll talk about soon. And then we can back out from the direct measurements of the densities and velocities and temperatures. We can sort of build up derived quantities like the rates of mass and momentum and energy addition to the plasma that are coming to again, heat the corona, accelerate the solar wind. These are more indirect. Okay, so now we're sort of transitioning over to the second part here of just a brief history of observing the solar corona above the limb. Of course, this really starts with total solar eclipses, right? That's the traditional way of doing that. And it's only possible because the sun and the moon have these roughly equal solid angles on the sky, even though they're very different intrinsic sizes. Is it a coincidence? Is it something anthropic? There's been some speculation that the equal solid angles have something to do with the roughly equal tidal forces that are exerted by the sun and the moon on the Earth, and the different phases of the solar and lunar motions might have excited tides in the initial tide pools billions of years ago that might have helped life develop. Very speculative, of course, but it's an interesting connection. People observing eclipses have been seeing them since ancient times. I've written here that it's wondrous, terrifying events for all of human history. There are some great surveys out there of historical eclipse observations. There's a fantastic book called Beyond the Blue Horizon by E.C. Krupp. I can give you links to it in the course material. Also, Doug Duncan at the University of Colorado Boulder is producing a MOOC, a massive online course that's going to be talking about the 2017 eclipse that's going to pass through North America, and he'll be having some historical information there. For now, I'm going to sort of start my history in the mid 19th century. That's when sort of photographs started to become available. But it took a while for eclipse photography to really get as good as the traditional means of recording them, which is drawing and painting. People see these things and they register on the human eye, and in some ways the human eye has a bit of a better dynamic range than the early photographic film that they were using in the 1800s. So drawings were actually better than photographs for several decades. You can see some examples here. You can see far out. You can see the so-called streamers that flow out into the solar wind. There was one in 1860 that was a coronal mass ejection. You can see in the lower right of Temple's drawing there, a twisted, compact knot of magnetic field that was flowing out through the corona that they happened to capture during the solar eclipse. Eclipse expeditions were a big thing in the latter part of the 19th century. Groups of scientists would travel all over the world to chase the eclipses. I've got a photograph from 1898 at the bottom there, showing an expedition to India, and of course also in 1919 an eclipse expedition was what helped prove general relativity by looking at the position and motions of Mercury very near and the positions of stars aberrated by gravitational effects near the sun. I did want to read an interesting quote. I know it's kind of strange to read it without putting the words up on the screen, but I didn't want to just fill your screen with words, but I thought it was kind of interesting. Henk van der Hulst did eclipse observations in the early part of the 20th century, and he had a very sort of nice reminiscence that I should read to you. He said that to study the corona and chromosphere requires a firm optimism. Though recent methods permit observations outside an eclipse, most of the data still come from eclipse observations. A year's preparation at home, a long journey, and a month's preparation on the eclipse site are required. Clouds may make all this work useless. If the sky is clear, some member of the expedition may contract malaria or break his arm. A motor may not work after many flawless rehearsals, or, in the excitement of the great moment, the person in charge may forget to take the cover off of the telescope. All of these events have happened. Less notable accidents, like a hazy sky or a poor focus of the camera or spectrograph, may be just as detrimental to the results. The primitive surroundings and the sharp drop in temperature before totality is reached make it quite hard to attain and maintain perfect adjustment of the instruments, and the second try may be many years later. So it seems kind of grim that they had to go through such things, and modern-day eclipse chasers still have to contend with a lot of those factors as well. But luckily, there are better methods now, and I'll be talking about them. So let me continue. When there is an eclipse, one of the first things that is observed is very near the solar limb. There's the solar chromosphere, this bright, mainly reddish band of intense radiation that you see at the limb. We now know it's due to 10 to the 4 Kelvin plasma or so that sits right above the solar limb. I'm indebted to Kevin Reardon of the NSO for collecting a lot of the old references to the chromosphere, because for some reason when talking about the chromosphere, people got very poetic. You can see a lot of the little quotes here, full lake red, blood red streaks, sierras, and saw teeth for a circular saw. Norman Lockyer, who I'll mention in a second, sketched some of the structures, flames and beams and streamers of the solar chromosphere. And it's just sort of a fantastic little artistic outlet that the scientists got to do when they would discuss the chromosphere. Now, the word chromosphere means color. It's the color sphere, the color layer above the surface. Traditionally, people have sort of interpreted that as just referring to this red that comes from the H-alpha. But there's evidence that Norman Lockyer, who coined the term chromosphere, was really referring to the full range of bright emission lines that appeared. And there's an example spectrum shown there. Not just the bright red H-alpha line, but also lines in all the other parts of the spectrum that appeared. So it's sort of the multi-color layer of the solar atmosphere that you can see with spectroscopy. Now, I mentioned Norman Lockyer. Now, he and Pierre Janssen in the 1860s and 1870s were the pioneers in doing a lot of this science. They noticed that there was this line in the yellow part of the spectrum that nobody had ever identified before in terrestrial spectroscopy, the analysis of terrestrial gases, and they discovered a new element. They discovered helium. They named it after the sun, Helios, and they realized that this was a new element, and they added it to the periodic table. They also kept looking at some of the other lines. There were some other unidentified lines as well. On closer inspection, they found a few other lines. There was especially one in the green at 5303 angstroms. I don't know if you can see it in the spectra up there, but there's an image of the green line corona. They didn't know what it was. Again, didn't correspond to anything. They called it coronium because it was prominent in the solar corona. And in 1869, Lockyer went on. No, he didn't do too much. He founded the journal Nature, and in its first issue, he had sort of an editorial about this green line, and he said that it was bizarre and puzzling to the last degree. And that bizarre and puzzling nature persisted for 60 years or so, because it took a while to really identify what these coronium lines were. Lockyer did a lot. He discovered helium. He discovered these other lines. He founded Nature. People started to sort of think of him as sort of feeling an ownership over the solar corona. I won't repeat this little piece of poetry that was published about him, but you can understand that people were feeling that Lockyer was sort of taking credit for a lot of things. But he did a lot of things. He actually accomplished a lot. I think this was from his obituary in 1921, but he was well liked, I think. But again, as I said, it took several decades until the 1930s or so for people to really identify what these coronium lines were. The atomic physics had to catch up. You know, we had to have quantum mechanics and predictive atomic physics to really be able to figure out. The coronium lines come from highly ionized atoms, highly ionized ions of heavy elements like iron and calcium. They're written here on this screen on the right with brackets around them. That's a spectroscopic notation to tell you that they're forbidden lines. They're not permitted lines according to the quantum mechanical line formation rules. We'll be talking about that later in the course, listing several of the coronium lines. There's also forbidden lines that are seen in the Earth's aurora. For a while, people were talking about aurorium or geocoronium, and also in nebulae in space, you know, emission nebula. And people were trying to identify these lines as due to some new element called nebulium as well. But again, they all turned out to be relatively mundane elements that are, that in some cases are ionized, and in some cases, and in all cases, are forbidden by the standard rules of the quantum mechanics of line formation. So there's some special things going on there. But we now understand them a lot better. And in the 1940s, it was really Hans Alfvén that sort of assembled all the different pieces of evidence together to come to an understanding that the corona really is about 1 million degrees, that there's this strange temperature inversion. The temperature goes up as you go above the surface, you know, further away from the heat source in the solar interior, the temperature goes back up again to 1 million degrees. And he cited these coronium lines that by then were identified by Grotrian and Edlane as these high ionization states. And you can only get these high ionization states if the temperature is high. There's been, in the 1940s, there had also been a lot of spectroscopy, some high-resolution spectroscopy of these lines. These lines had very wide widths. They had, you know, Gaussian-type profiles. The width tells you something about the temperature of the gas that's doing the emitting, and the temperatures are, again, were consistent with 1 million degree type values. Van der Hulst, in the 1950s, he sort of boiled this down to an exact science of looking at the radial dependence of the electron density, which you can measure from the brightness as it drops above the surface of the sun. And he found that if there was no solar wind, which they didn't quite know about yet, and the coronal solar atmosphere was in hydrostatic equilibrium, you could derive the temperature from that. And again, from this hydrostatic equilibrium, you get a temperature of 1 million degrees. We'll talk about that in a bit as well. There was also a more indirect piece of evidence, and that was that the Earth's ionosphere exists, that the Earth has this ionized outer layer of its atmosphere, and one of the only ways of producing it at that time, people thought, well, there's UV and X-ray radiation coming from the sun. There's time dependence. You know, after a flare or something, we see an enhancement in the ionosphere, so there does seem to be a solar connection. So how does the sun emit UV and X-ray radiation? Well, if there's a hot 1 million degree outer layer, that's where the dominant photon, the dominant photons of 1 million degree plasma layer is in the UV and the X-ray. So again, more indirect, but also consistent with the existence of this hot corona. Okay, we now know there is a hot corona. There was also this sort of parallel history of the gradual discovery of the solar wind as well. The gradual discovery that the sun is evaporating its outermost layers of plasma, and that those layers accelerate out to supersonic speeds and fill the solar system with plasma. So again, you can go back to the late 1800s. People started to see connections between solar flares and then things happening on the Earth a few days later. You know, enhancements in the aurora borealis. Problems with telegraph systems. You know, again, in the late 1800s, people were starting to crisscross the globe with wires, you know, with large-scale conductors, and those can be affected by weak currents that are driven from space. Geomagnetic storms, you know, when compass needles were start to go crazy, again, timed with things like solar flares. The astronomers were also getting into the picture by taking note of the many comets have two tails, one that sort of trails behind the comet kinematically, and the other one that's always pointed radially away from the sun. And something has to be blowing away from the sun in order to produce that material. I have another quote, another interesting quote. I'm not going to read it out loud. This one I will put on the screen for you, from 1859, of a telegraph event. It's kind of an interesting story where the geomagnetic energy was actually so strong in the Earth's lower atmosphere that it was allowing people to communicate via telegraph without turning on their telegraph batteries. They could actually communicate with this so-called celestial current. And you can read the transcript of a telegraph session there. The other interesting thing was that in 1895, Christian Birkeland in Norway was doing some fascinating laboratory experiments with magnetized plasmas, magnetized balls surrounded by ionized gas. And he found that the patterns of with a dipole magnetic field, the patterns of the gas on the surface of the planet, of the surface of this little ball, were very similar in shape to the patterns of aurora borealis on the surface of the Earth. So again, a very similar analogy was proposed there, that the sun emits cathode rays. And back then, those are streams of electrons. We now know it's a more balanced stream of electrons and positively charged. It's a neutral plasma, not just electrons. But again, very similar insights. Okay, then we're led up to the 1950s, of course, when Gene Parker at the University of Chicago put all these different pieces of circumstantial evidence together. And he also realized that the physics of this million-degree solar corona, that there's a high gas pressure, a high gradient of gas pressure, right? There's a high gas pressure near the sun in the corona, and it's dropping rapidly as you go out into interplanetary space. And high gas pressure gradients drive rapid motions. And again, I have this little cartoon of a balloon here, right? If you have a high pressure and you let the air out, there's a net motion of the gas where it moves from a region of high pressure to low pressure. That's essentially what the solar wind is, and he worked out mathematically that it should be this transonic transition from subsonic to supersonic flow in the plot there. The nice thing was that he only had a few years to wait, because he was doing this at the dawn of the space age. In the early 1960s, there were spacecraft that went out that were leaving the Earth's protective magnetosphere and sampling the pristine solar wind that was flowing by. It took until 1962 for Mariner 2 to really get out there with the proper instrumentation, and for a long enough time span to really get the confirmation that there is this continuous supersonic flow of particles that fills the solar system. Marcia Neugebauer and colleagues confirmed that in 1962. And really confirmed, discovered the solar wind and vindicated Parker's predictions, which were controversial in some circles. Okay, so where does that leave us, right? We have these eclipses where we can observe the properties of the million-degree corona and some aspects of the solar wind, but we really want to do better. We don't want to have to wait years and years for eclipses. We really want a consistent view of these regions where the heating is taking place, where the solar wind is accelerating, and where all these other bits of solar activity like flares and coronal mass ejections are also happening as well. So our goal is to observe the solar corona consistently above the solar limb outside of eclipses, right? That's where Bernard Liot comes in. He invented the solar coronagraph, and I just want to emphasize the spelling, coronagraph, right? Some people often say coronograph, or spell checkers might change it to chronograph, right? The fancy word for a timepiece. But no, take note of the spelling, coronagraph. Bernard Liot in the 1930s developed this instrumentation. He continually improved it throughout the remainder of his life. You can see the sequence of images here. Basically, this was an idea of a telescope with an occulting disk in the front of it that blocked out the sun. And then there had to be other stages at subsequent stages of the optical system to continually block out light that's diffracted around the occulter, and we'll talk about that in lectures 3 and 4. But you can see the gradual improvement of the observations from the 1930s to the 1940s, and now as we go into the 1990s and 2000s, the coronagraph technology got much better with space-based coronagraphs. This movie, which I thought would be repeating, shows you a sequence of coronagraph images. The white circle shows you the size of the sun, and the fact that the occulting disk is much bigger shows you that sometimes you have to block out more than just the sun to get a good to do a good job of observing the much fainter radiation from the side. We can see the solar wind and coronal mass ejections flowing out. Beautiful images like this, and we'll be talking about them as we go. The last little piece before I'm done is just to say that as we go into space, as we launch telescopes into space, that opens up regions beyond just the visible part of the spectrum, especially the X-ray and the UV. You know, that's where this million-degree solar corona is emitting most of its light. So that's where we really want to observe, right? So in the 1940s, you know, the U.S. had some repurposed German V-2 rockets that were used to you know, to mount some telescopes on, and tests from the White Sands Missile Range in New Mexico were done. There was a lot of detector development into the 1950s and 1960s, to the point where then there were some dedicated satellites. The orbiting solar observatory, shown here on a postage stamp, was launched in 1962, and several other orbiting telescopes were done that because they got above the Earth's atmosphere could easily observe the UV and the X-ray. Where I enter the story here comes with John Cole, who in the 1970s first developed an ultraviolet coronagraph spectrometer. So I sort of split up the acronym that he often used for these instruments: UVCS, ultraviolet to see where the photons are in space, coronagraph to block out the disk of the sun, and spectrometer to break up the light into its component parts. In the 1990s, I started working for John Cole's group at the Harvard-Smithsonian Center for Astrophysics. That was the time when the SOHO satellite was being launched. There was the so-called International Solar Terrestrial Program, ISTP. SOHO was a key part of that. SOHO was the Solar and Heliospheric Observatory with 12 different instruments on board. The UVCS was one of them, and I worked for that team for several decades at SAO before coming to Colorado. And I'll be talking a lot more about the science there. And that essentially brings us to the end of our first lecture. So next time, I'll be taking a little detour into defining some of the properties of the radiation field, and then we'll talk more about coronagraphs. You know, why do we need to block out the disk of the sun, and what kind of things do we need to do to really get rid of that light so we can see the much fainter radiation from the corona? Okay, that's it.